Hello, welcome to this lesson in the Chemistry Tutor. Here we're going to conquer one of the most central things that you're going to learn in chemistry, certainly when you're studying the gas laws, and that is the ideal gas law. So here we're going to introduce the ideal gas law as an extension of what you already know, and so by now you probably understand the significance of where we're going, at least from a big picture point of view. First, we started looking at these individual laws like Boyle's law and Charles' law and Avogadro's law. Then we combined them all together and we found something called the combined gas law. And those laws were very useful when you're going from state 1 to state 2. And that means, you know, I have a certain amount of gas, certain volume, certain pressure, certain temperature, and then I change something. So state 1 was the initial state, I changed the temperature or I changed the pressure, and then I want to know maybe what the volume is or something in the final destination state. So going from state 1 to state 2, those are basically the kind of problems we've been doing so far. But the ideal gas law is kind of is an umbrella over everything we've learned so far. And so when you understand the ideal gas law, you'll be applying it to problems throughout chemistry for a great many type of problems. So in order to understand where it really comes from, remember, so I'll just say up here, recall, something that we learned in the very last section. The combined gas law was P1V1 over N1T1, and we said that no matter what gas you have, if you know its pressure, its volume, the number of moles, and its temperature in Kelvin, and you do this calculation, you're going to get a constant. All right? And this constant was going to be true no matter if what combination of variables we have. If you change the pressure, change the volume, then the new temperature or whatever it is that you obtain, if you recalculate this in some other state, you're going to get exactly the same thing. So P2V2 in some other state is N2T2, like this. So that's what this is intended to represent. No matter what state you subject your collection of gases to, if you know the pressure, the volume, the temperature, and the number of moles, and you do this calculation, you're always going to get the same number. But I told you that it didn't really matter what that number was in the previous sections in the combined gas law, because ultimately what we did is we kind of take it out and we make these guys equal to one another, and then we use the relation that we did for the combined gas law. So this was called the combined gas law, and we've already studied that. We've already done problems like that. Okay, but now what we want to do is we want to derive what we call the ideal gas law. So we really want to find this constant. We want to solve for this constant. And what you're going to end up finding is it's going to be called the universal gas constant. Okay, so we're going to call the constant capital R. You'll see that in your chemistry book. We want to call this gas constant R, capital R. Okay, and so the question would be, if I asked you, how would you find what this constant is? How would you be able to do that? How would you be able to calculate it experimentally? If you're trying to calculate the universal gas constant, how would you do it? Well, the one way to do it is basically just to kind of recognize that the universal gas constant R, this thing right here, is equal to PV over NT. So literally, if you go in the laboratory and you know that you have somehow already ahead of time maybe 1 mole of gas or 2 moles of gas, but if you know what N is and you know exactly what the temperature is, and if you can measure the pressure of the gas and exactly what the gas's volume is, then if you calculate this thing and put in the numbers and divide it, then the answer you get is, by definition, what we're saying is this constant number called the universal gas constant. Okay, so clearly when you do this experiment, you have a couple of choices. Now, the number of moles